Alrighty, welcome back AP Chemistry students. Let's go ahead and start set 7 here. The set 7 will be in two parts. It's all about nomenclature, which is giving names to chemical formulas. We will convert between the name and the formula and the name. Let's start with the very first type of ionic compound, the very first type of naming we can do, and that's naming the type 1 binary ionic compounds. You should already know by now what a binary or what an ionic compound is, but the word binary means two. So only two different types of elements will form. We won't do three. So for instance, you won't see like a potassium binding with a bromine and a krypton. We'll only do things like potassium and bromine, two different elements. There are three basic rules for naming type 1 binary compounds. The first one is the cation goes first in the name and the formula. So when we're writing a formula or a name for a type 1 binary compound, whatever ion is positive, which is going to be the metal, is going to be listed first. The second rule, the anion goes second in the name and the formula. So the negative ion, the non-metal, will be listed secondly. Number 3, the suffix of the anion is changed to IED. The suffix is like the last 2 to 3 letters of the original name, and we will knock off those last 2 to 3 letters for the anion only and replace it with IED. That's why you're used to hearing things like sodium chloride instead of sodium chlorine, sodium chloride. And lo and behold, that's actually our very first example here. NaCl, this is practice or examples with naming compounds where we're going from the formula to the name. So the formula to the name. As you can see, the metal is listed first, Na, which stands for sodium, and listed secondly is chlorine. But because the third rule says we will omit those first 2 to 3 letters, or the suffix, in this case the ine, we'll kick those out and replace it with IED. So NaCl becomes sodium chloride. That's pretty straightforward. Next up, let's do potassium sulfide, K2S. Potassium is listed first because it is a metal, okay? And notice we didn't change the suffix for the metal because it doesn't say to do that up there. We list it first. Listed second is the non-metal, and it's sulfur. But because it's the non-metal, Rule 3 says we must change the suffix to IED. So we'll knock off the UR and place it with IDE, and then we have potassium sulfide. Potassium sulfide. Alrighty? Going from the formula to the name is pretty straightforward as long as you can remember those 3 rules. However, going from the name to the formula is a little bit tricky and requires a little bit of in your head math, and it's not too difficult, really it's not. But let's go ahead and take, for instance, the rubidium oxide. When we're going to convert between the name to the formula, let's start with getting the symbols first. So pull out your good old-fashioned periodic table and find rubidium. There it is right there. And we are going to write it down RB. Now, when converting between the formula and the name, you are going to need to figure out what the charge on a rubidium ion will be, or what the charge on any of the positive ions will be. Because rubidium is in group 1, it has 1 valence electron, and it's going to lose that 1 valence electron. And if it loses something negative, it's going to become positive, obviously. And how many negative things is it going to lose? Well, it's going to lose the 1 electron, so it's just going to be positive 1. And you don't have to put the 1 behind the positive in that case. You can just leave the plus there. The 1 is implied to be there. Let's do oxygen next, or oxide. Oxide comes from the element oxygen, and everybody knows what the symbol for oxygen is. It's O. Let's go ahead and put that there. Now we need to figure out what the charge on oxygen is going to be. We know it's a non-metal, so it's only going to form a minus charge. And we know that because it is on the non-metal side. So how many valence electrons does oxygen have? Well, it has 6. How many does it need to gain to get to 8? Remember, all elements are trying to get to 8 somehow. It needs to gain 2 to get to 8. Okay? So it is going to gain 2 electrons, and because electrons are negative, it's going to be a -2 charge. Alright? Now, to make the final formula, literally all you do is you're going to take the superscripts of the charges. These are the superscripts, and they are going to become the subscript of the other ion. We call that the crisscross method. So this 1 down here is going to go here. This 2 down here is going to go here. We're not going to bring the charges, we're just going to bring the numbers. So it's RB2O1, and you don't have to put the 1 there, it's implied to be there. Why do you have to do it this way? Well, ionic charges have to have a net 0 charge, okay? That means when you add up all the pluses and minuses in the compound, they have to come out to 0, all right? Let's determine that mathematically. We have 2 rubidiums, and each of them has a +1 charge. So that's going to be +1, +1. There's 1 oxygen in the formula, so how many, what's the overall negative charge for the oxygen side? Well, there's only 1, so it's going to be -2. If you add all of these together, +1, +1, and -2, you get 0. And we know our formula is correct. By adding up the charges at the end of the formula, you can check to make sure that you did that formula correctly. Let's do aluminum oxide. Aluminum oxide is going to be a little bit tricky, a little bit different. Take a look at aluminum here. It has 3 valence electrons. Now, aluminum is a metal, so it's going to lose those 3 valence electrons. So we know aluminum is going to have a +3 charge. Oxide, same thing that we did for the rubidium oxide. You already know that it's going to be -2. And then taking just the numbers, we're going to do the crisscross method. This time I actually crossed them. And our final formula is going to be Al2O3. Let's check ourselves mathematically to make sure that we did this correctly. We have 2 ALs in the formula, and each AL contributes a +3 charge. So +3 charge for those 2 ALs. In the formula that we wrote, there are 3 oxygens, each contributing a -2 charge. So that's going to be -2, -2, -2. If you add all that together, +3 + 3, that's +6. -2 + -2 + -2 is -6. +6 + -6, 0. Our formula is correct. So there you go for the binary compounds. Why do they react this way? Well, there's a specific law down here that's called the law of definite proportions. Chemical compounds contain the same elements in exact proportions by mass. In other words, what that means is they will react in such a way that their charges come out to be 0. That's about as simple as I can put it. 2 rubidiums have to react with 1 oxygen in order to balance out the -2 charge. Same thing over here, you have to have 2 molybdenums for every 3 oxygens if you want to make an aluminum oxide compound so that their charges can balance out. And we're dealing with mass here. If we were dealing with something in grams, then these would still work out to be pretty much the same way. We'll look at more advanced ways of figuring out formulas later on in the year. Let's go to the second type of binary compound, and that is the type 2 binary compound. These are a little bit more difficult to understand. I might have to go into a second video for this one. Okay, so I'm running out of time. Type 2 binary compounds or ionic compounds, they have the same rules as the type 1s, but there's an extra step because the type 2 binary compounds use the transition metals, and transition metals can have a different charge depending on which transition metal it is. For example, iron can either be +2 or +3 depending on what it's bound with. And if you have forgotten where the transition metals are on the periodic table, it's this whole center group right here. Let's look at an example, or the fourth step would be this extra step right here. When writing the name for a type 2 binary compound, you have to include a Roman numeral next to the positive ion, and you need to put that Roman numeral in parentheses because that will dictate what the charge on that positive ion is. Let's look at an example, okay? CuCl, copper chloride. Okay. We need to write a name for this. We're going to go from formula to name. Well, we know that Cu is copper. You could get that from the periodic table, but we don't know what the charge on that copper is going to be. Okay? We don't know just yet, but we'll figure it out. The next one is obviously chloride. Remember, the rule still applies. You have to change that INE to an IED, and that's the nonmetal, so it's going to be listed second. How do I figure out the charge on that copper ion? Well, in the formula, I only have one of them. Okay, and I know that the charge on chlorine is -1, or chloride is -1. So if chloride is -1, what charge does copper need to have to balance out to become 0? It needs to have a +1 charge, so we will put the Roman numeral 1 down here, and this formula is called copper 1 chloride. Let's do the next example. Fe2O3, an iron oxide. What type of iron is it? I don't know. Let's figure it out. We know that Fe is iron. I don't know what charge it has just yet. And oxygen obviously is oxide. Now this one's going to be a little tricky. We know that the charge on oxygen is -2. But we have 3 total oxygens on this side. So what is the overall negative charge if we have 3 -2's? It's going to be -6. Okay? Which means over here we have to have a +6 charge to balance that out. But is the iron +6? If you said no, then you are correct. The iron on its own is not +6. We have 2 irons total. Okay? So how does a +6 charge equally divide into 2 ions? What is the charge on each ion? +3. So this is iron 3 oxide. Iron 3 oxide. You can do these 2 examples right here on your own. I now would like to switch over to doing the name to formula, and we only have a few seconds to do this one, so it'll be pretty quick. Tin-4 chloride. If you look at your periodic table, you'll know that tin is Sn, and you know that it has a +4 charge. You know that fluorine is in there as well. Put +4 here. And it has a -1 charge. It's in group 7. Needs to gain 1 to get to 8. If you do the old switcheroo method, you'll have SnF4. Okay. I'm going to pause this video here. We'll do copper 2 sulfate in part 2, as well as the naming covalent compounds. We'll see you there.